In my last video, I looked at railguns. Now, whilst I was reviewing the footage, I started wondering how they filmed the projectiles in flight. These are not the typical sort of high-speed camera shots where you see a bullet hitting a target, for example. These are tracking the projectile from the barrel down the firing range. From the footage, it looks like the camera is panning around and following the projectile, but that would be impossible. The tank round is travelling at over 1,500 metres per second and would normally look like this. For all of you out there who said it's done with mirrors, then you are absolutely correct. It works by having a computer-controlled high-speed rotating mirror in line of sight of a high-speed camera. The speed of the rotation of the mirror matches that of the object being followed, so the faster the object is travelling by the railgun projectile, the faster the mirror will turn to keep up with it. Using this method, the object can be kept in the field of view for 100 metres or so, or about 90 degrees of the mirror's movement. In this example, the Tracker 2 from Specialized Imaging, you can see the mirror and to its left where the camera is. Because the mirror is computer controlled, it can be programmed to follow objects and accelerate either linearly or non-linearly. Now, rotating mirrors aren't new. In fact, they were some of the first high-speed cameras and are still some of the fastest in the world, capable of up to 25 million frames per second, and were used to record atom bomb blasts. During the Manhattan Project to develop the first atomic bomb, they required cameras that could record the first few microseconds of the explosion. In order to create a nuclear chain reaction and achieve critical mass, a baseball-sized piece of plutonium had to be compressed to about half its size. This was achieved by using an array of focused high-explosive lenses surrounding the plutonium core. In order to make it work effectively, the explosives, 32 of them in all, had to be triggered within 1 microsecond. If any were delayed, then the compression of the core would be unequal, and the reaction would either be much less or may not even happen at all. Using a super high-speed camera, it would be possible to see how effective the explosive lenses had been just a few microseconds after detonation. At the time, the fastest cameras were Fastac Cine cameras and could achieve around 10,000 frames per second, or 1 frame per 100 microseconds. This still wasn't fast enough, though. The first high-speed rotating mirror camera was the Marley, invented by the British physicist William Gregory Marley. The Marley camera used a rotating mirror and an array of lenses inside the curved housing, each focused onto a single piece of film around the edge of the case. This could record a sequence of
the pin chip configuration. Once you get pretty programmed out, you know what the entropy of those hots and lows are.
By the time
you get it to run that loop through that system, and again, you know, we know the system, you know the system. Here's the 10-foot rail, gravity, uranium, plutonium,
said that the fixed short focus and low quality of the lenses
something else means if it does diverge this way, and those are the measurements.
He helped develop the Mac Streak camera, which had a 10 million frame per second limit. That's 1 frame every 100
between frames, it did this. It
By the
goes
1950s,
changing
however,
fields,
Egerton
flipping over in wave functions, banging off the stuff that
named
augments it to the point where entropy changes it over,
This used
but
a
other things are colliding into it at the same time
which
without
allowed it to have an exposure
reducing
time as short as
the volume
10
of that box in such a way.
as 10 billionths of a second. This was first used for the hydrogen bomb test of the Eniwetok Atoll in 1952. However, they only took 1 image. So to see the first few microseconds of a nuclear detonation, up to 10 were used in sequence with an average exposure time of 3 microseconds. The images were then played back and blended together to give the impression of a film. For the British nuclear tests, the Atomic Weapons Research Establishment created the C4, a huge rotating mirror camera weighing in at around 2,000 kilograms and was the fastest in the world at the time. This could record up to 7 million frames per second, with a mirror rotating at up to 300,000 revolutions per minute, and recorded the first British atom bomb test on the 3rd of October 1952. The rotating mirror cameras are still in use today, but now they use highly sensitive CCDs to replace the film strip. The Rand RS-128 and Cording Model 510 have 128 CCDs and a
Yep.
gas-driven
That's what it
turbine
is.
mirror
I'll be damned.
driven by helium to
Clean up.
achieve up to 25 million